I'm a program manager on the Cosmos DB team. And the title of today's talk is Modeling Data and Best Practices for the SQL API for Cosmos DB. Now, why do we care about data modeling? When I was in school, I took a class about databases. We used Postgres. How many of you have done the assignments where you have like a workload, and then you have to write a schema, and then the assignment has to be completely normalized? Yes? OK, and if you have any duplicate data, the professor's like, no, 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 that's wrong. It turns out, when I started working on the Cosmos DB team and started working on this NoSQL database service, that the way you think about modeling data is actually completely different. And it's not just a philosophical problem of NoSQL versus SQL. The way you model data in a NoSQL system also has a huge real-world impact on both your performance and your cost. So performance in the sense of how fast are your queries, how fast are your writes, how fast are your reads, what throughput are you getting? And of course, cost in the sense of money. It's something that we probably all care about if you're an organization that worries about IT costs. So in Cosmos DB, or actually in any database system, if you duplicate data, that takes up more storage, which depending on the pricing model might incur more costs. At the same time, in Cosmos DB, it's also billed per collection. So if you have lots of small collections, then your costs will add up as well. So really understanding how to work around data modeling to best optimize your system and minimize performance and optimize costs. All right, it will be the subject of today's talk. All right, so how many of you have used Cosmos DB before? OK. How many of you did it in like a proof of concept, trying it out kind of stage? OK, keep your hands up. How many of you tried it out and then actually went to production? OK, so some drop off there. And then how many of you tried it out and did not go to production? You're like, this thing just won't work. OK. All right, so hopefully I'm going to give some tips and tricks for really things at both at the proof of concept and in production stage. I'll start with the proof of concept stage, where you're evaluating the system. There's a bunch of choices you need to make up front that if you do well, you will have a happy time with Cosmos DB. And that's really the goal of this session here. All right. And for those of you who walked away, hopefully some of these best practices might help you, encourage you to take another look. All right. So today, quick intro on Cosmos DB. How many of you are familiar with Cosmos DB already? OK, so I'll do a very, very quick intro. I won't spend too much time on it. I'll go through some data modeling strategies to address some of the common questions and challenges around how do I model data in this NoSQL schema, NoSQL system, especially if I'm coming from a relational background. We'll talk about the strategies for choosing the right partitioning key, which, in my opinion at least, right after data modeling is the next most important decision you'll have to make about how you set up your Cosmos DB instance. And then finally, time permitting, I have some topics about how to optimize Cosmos DB after you've sort of set these two. If you run out of time, please see me afterward. I can definitely walk you through the content. It's a 45-minute session that we ended up getting. All right. So Cosmos DB is Azure's globally distributed multi-model database service. And if you're wondering why you would want to use Cosmos DB, it's because it guarantees a lot of great things that you'd only get in a service running on Azure. We have turnkey global distribution. So you're now able to read and write data to any region in the world, which is really great for low latency queries and low latency writes. At the same time, we also promise elastic scale out of throughput. This means theoretically, you should be able to scale your container collection from gigabytes to petabytes, handle tens of operations per second to even millions of operations per second. We guarantee low latency at the 99th percentile. We have 5 well-defined consistency levels to help you make the right trade-off for your application. And we also have SLAs around all of these. Now, Cosmos DB is a multi-model database, which means that we support multiple data models, most notably key value, column family, document, and graph. And on top of them, we have these APIs you're likely familiar with. You can store data in Cosmos DB and query it as if it were a table, Cassandra, SQL, MongoDB, or a Gremlin database. Title of today's talk is SQL API and document, so everything here will apply here. If you have questions about the other ones, see me afterward. We can talk about them. All right, so data modeling. Quick note about data modeling. Sometimes when you hear NoSQL, you kind of get the feeling, it's okay, data modeling goes away, no more schema, everything is really free now. But in fact, it's just as important with relational data. The only difference is there's still a schema. It's just really implicitly enforced by your application. If you add a property that hasn't been defined anywhere else, no system is going to stop you. And it actually might be exactly what you want to do, but your application will have to know about it. And especially in the way you write your data access layer to write those queries. So the idea here is that if you plan this up front, then you'll have the best performance going forward. Now, the two extremes when you model data is the one is if you're really familiar from a SQL background, you might just normalize everything. No duplicate data. Sometimes the extreme of that is you want to do one simple query, and then you end up joining around 3 or 4 tables, and you're like, why isn't it just all in one place? Has anyone run into that? Yeah. At the other extreme, you could just dump everything into the same document. It's kind of the embed as one piece, come as you are, which is really great because now you just do one query, everything is there. But then the next time you want to update one small field and you have a giant document, you're like, why do I have to update this entire document? Why can't I update my nice one order table with 3 columns and an ID and just update it there and all of the references propagate? So these are some of the considerations and challenges you might run into when you start thinking about how to model your data. So to make this more concrete, as opposed to those lovely hamburgers, in a SQL world, you might have, if you were trying to model a restaurant menu, so you have a menu item with a name, description, category, and then you have a separate category so maybe it's like the seafood category or the breakfast category. I'm very hungry, as you can see. And in NoSQL, and in this model, each menu item is going to have a reference to a category. So you never repeat that data 2 different places. On the other extreme, if you wanted to embed everything, you could have each item as a self-contained document. So you've got hamburger, and then you know it's in the category of sandwiches, and it's right there for you. So the real question when it comes to modeling challenges, I think you can talk about the challenges in an abstract sense, but at least the gut feeling I got when I first encountered NoSQL was, where are my joins? I want to do my joins. It's a question I've been getting a lot at the booth as well. But really, if you think about what's underlying that question, it's really, I need to get all the data in the same place. And the nice thing about the NoSQL is you can actually do that if you model your data intelligently. So the two main, and a nicer way to put it is, should I normalize my data or de-normalize it? Should I embed everything in one document, or should I have references to other documents that contain information I might need? And the other challenge or consideration you might have is, should I put data types in the same collection or in different collections? So if you think about in SQL, you have one table, maybe it's for customers, and you have one table for orders. The only entity in the customers table is a customer. You would never put an order in that because that's just not the right thing you would do. But actually in Cosmos DB and other NoSQL systems and document database stores, you can put anything in those JSON documents. So our database doesn't know if it's really morally a person or an order. They can actually all live in the same collection, which feels very weird. But if you're coming from a relational background, but sometimes it's actually a really nice thing to do, as we'll see later in this talk for some very use cases. So more concretely, first one is you're embedding everything. Second one is you're referencing with 2 different types of separate documents. So in this first section, I'm just going to go through some guidelines of when you should embed. One thing to know about data modeling is there's no precise science to it. There's some guidelines, but really the best way to find out what's right is you do your proof of concept and see, is it actually working for my system? All right, any questions so far? Okay, please, yeah. Oh, is that a question? No, okay. All right, so the first guideline of when you should embed. I remember my 3rd day of Cosmos DB, my manager was giving a presentation. He said, data that's queried together should live together. And I thought it was such a nice phrase that I even remembered it for here. And the idea is that for some documents, if you just think about the real world, they always live together. So for example, if you have a recipe, the ingredients are always queried with that document. You would never want a recipe and not want to find the ingredients. So if you have that kind of model, that's a good sign that you should embed them together. In a similar way, if the child data is dependent on a parent, so for example, if an order processing system and you have an order that's ordered by a customer on a certain date, if you're looking for an order, you almost certainly want to know what the items were. So that really makes sense to embed them in the same document. For example, you could reference these items ordered into a separate items ordered collection or SQL-like table. But if you did that and you're looking for an order, then you're almost guaranteeing you have to join every single time. So in that sense, if the child data is dependent on the parent, that's also another good sign that you should embed. Okay. Same way, if there's a one-to-one relationship between the data, which means it's almost the same as the first principle, but if you think about it, for something like a customer profile, you know you'll have a name, you'll have an email, phone, they have a loyalty number, they're only going to have one of these fields, and you're almost always going to want them together. And even for something like addresses, maybe you split it out into a separate table because in a SQL world, because you don't want to have too many different separate fields in the same one table. But the thing is, the address doesn't really change that much. So if you need to update it, then you just update it all in one place. It's not too bad. Okay. Let me clarify what I mean. So another case of when you want to embed is if you have a similar rate of updates. So ideally, if the data changes at the same pace, as in it changes pretty infrequently, then that might be a good time to embed. So for example, here I was talking about addresses. Person could have more than one address. We all move from time to time. But if you think about your database system, you can think of that as a much rarer event than other things like suppose ordering or commenting on a system. So that's another time where you just might embed it. And it's true, if someone updates their address, yes, you'll have to go reference their entire customer profile, but it's rare enough that it should be fine for the trade-offs of your application. Okay. All right, so these are just some of the guidelines of when you'd want to embed data. And the real thing here is when you embed data, as you might expect, it gives you better read performance. So why does it give you better read performance? Because all your data is in one place. You make one query to your collection. You get it all back in one time. But the trade-off, as you know, the real world is full of trade-offs, is that there is a potential trade-off to write performance. And the way you want to minimize this is basically only embed when you have these principles or guidelines be true. So the trade-off comes, suppose you have a really, really giant document. Your read performance is great. You query it. You get the fields you need, one network call. But if you end up having to write to it, and you have to write to it a lot, then all your read benefits have just kind of been sunk away from now the increased write latency. But if you don't have to write that often to it or update, then that's great. You've kind of minimized the trade-off on that end. Okay. Any questions so far? I can't really see in the back, but please shout. All right, so I'm just going to do a quick demo of what a query even looks like in Cosmos DB and show you what it looks like just to run a simple query. Okay, let me switch over to my machine. Okay. Can all of you see this okay? Do I need to zoom? Zoom? Okay, all right. Okay. All right, so here I've navigated to my data explorer in Cosmos DB, and it's just a view where I can see all the data in my collections in this account. So I have the hierarchy here is you have a database and then a collection, which you can think of in the analog of SQL as a table. And inside my collection, I have documents, and each of them is a JSON document, as you can see here. And this would be your analog to like a row, except it's a JSON document. Now, one question we get a lot is, how do I query this thing? Do I have to learn a completely new language? And the nice thing is it's actually very similar to the SQL syntax that you're already very familiar with. So for example, here I have a document. Actually, someone give me a number between 1 and 8. 7? Okay, 1, 2, 3, 4, 5, 6, 7. Okay, great, I'm already here. Thank you. You didn't know I was going to start at 1 indexing, did you? All right. So let's just write a simple query. I'm going to do a new query, SQL query. Okay, so let's just write a simple query where c dot customer ID is 12. Okay. All right, and as you can see, it's just a very simple query with a filter condition, and I get this document back. As you can see, let me go back to this. As you can see, we have a nested structure here where there's a customer ID, there's some profile data about them, but they also have a company and where they work. And the assumption here is that if you always want to know the company where someone is working, then just keep it in the same document. Maybe you have a separate collection somewhere else that's just only company information, but why do that join if you know you have to do it every single time? Or why do that separate network call to get it if you know you need it every single time? So that's how you write the data here. I'm just going to go into Visual Studio and just run the query from the SDK just to show you how long it takes and how great it is I can actually embed this all in one place. So switching over to Visual Studio. Okay, so all right, let me zoom in a little bit as well. Okay. Can you all see this okay? Yeah. All right. Okay, so here in my program, I'm just going to run this embed query embedded collection, which I'm just going to run the same query against that collection that you just saw. All it's going to do is it's going to have a stopwatch where I time how long it takes. And the query I'm running this time is I'm selecting a few properties, name, customer, customer ID, and the company, where a customer ID, I think we did 12 in the last case. 12. And all it's going to do is run the query via, well, it's timing the stopwatch and print out some of the results. So I'll go ahead and run it. And before I run it, how long do you think this is going to take? Sorry? How many documents are in here? I think there's around 100 in here. It's pretty short. 10 seconds? All right, I'll have you know I'm wired on Ethernet here, so. All right, I should tell you that this VM is running an Azure data center that is co-located with the Cosmos DB account. These are both located in West US, which is probably explaining the VM latency here, but the Cosmos DB data and this application are very close to each other. Yeah, so I'll run it. Okay, so as you see, it's found the ID. It's actually been able to query this in 5 milliseconds. This is the latency between the application and the Cosmos DB account. And if you think about it, if 5 milliseconds is all you're getting on that layer, then if you're optimizing performance, you might worry about the client at that point. But this is really great because we've embedded our data in one place. And imagine if you had to do 2 separate network calls for this. You make one call to the customer, get their company ID, make another call to get the company information. You resolve them on the client side. That's 5, maybe 10 milliseconds for the data, and then you have to do the logic on the client side. And then it might not be bad for one or a few requests, but if your system is under heavy load, then that all will add up. All right. Okay. All right, any questions so far? Yes.
What if you have multiple read models like the divergent parent-child relationship?
Mm-hmm.
You have some cross-cutting, like
yeah.
your recipe. I want to know all recipes, including lettuce. Like both of those are common.
Yeah. Like, what do you do?
What do you do?
Yeah. So so your question is, you have something like a recipe, and you just want to know something where there's a property or like a value that's common to a lot of them, and you want to query based on that, right?
Well, 2 queries. Like some people want to query recipes, like you said,
Mm-hmm.
but then you have to support other read levels, like cutting across.
Yeah. I'll actually show you a thing where you can actually have if you have data of different types in the same container, And the great thing about Cosmos DB is that it's actually automatically indexed. So even though, I'll get into partitioning later, but each field will be indexed. So if someone is searching on this property, someone's searching on this property, those are still indexed, so you'll still get the benefit of that as well. I think I'll have a section that will go into more detail about how to answer that question. Cool. All right, back to slides. OK, so that covered when you might want to embed the data. And now we can talk about when is a good time to reference the data. The first one is when you have a one-to-many or unbounded relationship. So for example, let's say you have an ordering system, and your company is doing so well that people are ordering every single day, maybe even every single hour. And your document model, as you had it to begin, is you have one person, and then you have all their orders in the same document. Now, it's great for the view where someone goes to the page, say, show me all my orders. You have them all in one place. But as they keep ordering and ordering and ordering, then that document grows really large. And every time they add a new order, you have to update this increasingly large document. So instead, because you know that the relationship between the person and the orders is unbounded and potentially high, might be a good time to reference. So instead of putting it in the same document, instead, you might have two different types of document. You have one for your customer, and then a separate order, where you have an order ID and an array of orders, where you use this to reference. So then in your page that serves like the list of all my previous orders, then you make one call to the customer, get the array, and then make the calls to get that data. The benefit, though, is, of course, when you add a new order, all you have to do is make a new smaller document here, and then update the reference here. Okay. Likewise, when data is changing at different rates. So earlier, we had data that was changing at the same rate, like name, email, address. But if you have aggregates, things where you're like the total money spent or the total number of orders, and the number is ticking up, you don't want to be constantly updating that and trying to serve very common reads of that data at the same time for some other use case. So this will also be a good time to reference that. So instead, you might have a stats and then a separate aggregate view of the information. So when you actually need the aggregates, you just query for that. And then otherwise, when you're just showing profile data, you don't need to worry about that data being in there. Okay. The other one is many-to-many relationships. So for example, this should be all dear address because we are here at Ignite. If you think about it, I'm only speaker here, but some sessions have 5 or 6 speakers, right? And some speakers have 5 or maybe not 5, but 3 or 4 sessions, right? So you have a many-to-many relationship between the sessions and the speakers. So one idea of what you could do here to data model it is you could have your speaker profile, and then just have a reference to the sessions that they are in. At the same time, in each session, you can also have a reference back to the speaker that they are in. So this link here and this link here. Okay. Another time when you want to reference is, and this is a fun phrase to say, when what is referenced is heavily referenced by many others. So let me give you a concrete example of that. For example, how many of you have used the app where you like star the session and then that's how you know what you're going to do during the day? Yeah. So imagine if you have to data model that. You have your speakers, you have your sessions, and maybe you have a concept of for each profile, each person, you have bookmark sessions. Now, if you are bookmarking lots of sessions, and there's so many sessions, you don't want to be bottlenecked on every time you bookmark having to update your entire profile. Or you also don't want to have a list of bookmarks for each session that could be like, theoretically, every single person in this attendee list bookmarking the same session. So instead, so here, the session is referenced both by lots of attendees who are bookmarking it, but also still the session is being used by the system to know who is speaking at which session. So instead, what you can do, this is a good time to reference as well, where for your speaker, you can use that same speaker ID link to reference the sessions they're in. But for the bookmarking system, just use the same thing to reference those sessions. All right, so in summary, these are some of the times where you may want to reference. And typically, as you can see, this will provide better write performance. Because now, if you have lots of writes happening to one type of data, then you just write that, and you don't have to worry about updating any giant other documents. This is the reference plus the document itself. But the trade-off then is that it might require more network calls to reads. For example, you make one call to get the customer profile, and another call to get the references. The great news about Cosmos DB is you can actually model your data in a way. I'll teach you how to minimize even that trade-off as well. And before I go on, I should say, but wait, you can do both. Sometimes you can have everything you want, sometimes, not all the time. But in this case, it's not a black and white where it can only embed or only reference. Sometimes you can do both depending on your use case. So for example, if you know for a speaker and they have a session, well, if you're looking at a session, sometimes you like to see who the speaker is. And if your session model, data model, only has the name and like speaker IDs, then every time you know, you'll have to go find the speaker information. But maybe you can just put the ones that you know people will want. So I know in the Star app, you click it, it has like the name and maybe their email address. But it doesn't need to show you like the phone number or the address or where they're from or anything like that in that short description. So in that way, you can data model to have the ones you know you'll frequently reference in that same session document, and then just still have the reference that you might need if you want the full view of their profile. As you can see, there is some duplicate data here. I now have name in the session, and I have name in the speaker. And this would probably be really weird in SQL. The professor would be like, no duplicate data. But here, it's actually just fine. All right. OK, any questions on this first session? Yes? Yeah, so it is definitely a trade-off. It is true that you then have to make sure that you do update that reference. So yeah. So in Cosmos DB, you can write your own custom trigger, which will be written in JavaScript. And if you need to do an update, you just make sure, OK, do this update, but also call this trigger. And the trigger can validate, OK, is this thing still true? Update this downstream thing. If not, then just fail. OK, yes? Yeah, that could definitely work. So you're saying the hot path is where you have like just the latest one, or you're just always writing a new document and you only care, yeah. Mm-hmm. Mm-hmm. Yeah. Yeah. Yeah, that could definitely work too. Just kind of this like append only kind of idea. Yeah, that could also work. Yeah. Cool. Yes. Yeah. So this is the thing where, at least just from the database level, we don't, since there's no strict relationships that you've defined, it's all kind of based implicitly on what you name the properties and what your application knows to do. So this is the case where you would want to write your own trigger to make sure that it is validated the way that you need correctly. Cool. All right. So I'm going to move on to this. To the next section, which is around, should I put my data in the same collection, or should I put my data in different collections? And for this one, I'm just going to jump straight to a demo. All right. All right. So if you put if you put the same types of data in the same collection, then you'll get a performance improvement in the sense you only have to do one network call. So it's a bit weird to think about abstractly, so I'll just give you a really concrete example. Going back to my portal, I have a collection, I have two databases here. Okay. This is in a weird order now. There's database 1 and then database 2. Ignore this thing in the middle. I don't know how I got here. All right. So in my first database, I have a customers collection, and I also have an orders collection. So customer is just customer profile. Let me zoom in. Okay. Customer profile, and then orders It's just the order with a reference back to the customer ID if needed. All right? So if you're just starting out from a non-relational background and you have orders table today, customers table today, this is a very natural way you might start out ordering your data. But I'll let you know that you can even do something like put these customers and orders in the same container. So here, my database 2, I just have one collection. And this document is the customer, type. And I've defined for each document, I've added a new property called type, where it'll either be a customer or an order. So if I filter to just order, okay, so now I haven't moved collections, I still have orders here. So why is this good? It's good because now I can do something that gives you the same benefit of join without you having to actually make separate network calls to do the join. All right, so let me just give you a quick demo back in Visual Studio. Go over to my demo. All right. Okay, so I'm going to run two simple scenarios. The first one is I'm going to query for the first database where you have the customers and orders in separate tables or in separate collections. So all that's going to do is first I'm going to First, I'm going to query for the customer info, and then I'm going to query for all their customer orders. So this is, and then imagine that there's some other logic that resolves them into the view that maybe a web app would see. So again, this will just be a stopwatch where it'll time how long this takes. Okay. Okay, so as you can see, it's about taking 8, 9, 10 milliseconds, which is about basically the two calls to Cosmos DB. We saw the first one earlier demo was about 5 milliseconds. Now it's just being doubled. But, and this is the use case, again, where you just want to get all the orders for one person. But now, because we have another scenario, we have the order and the person in the same container, then we can actually just do one network call. So let me run my other query. And the only thing different about this query is now it's still going to say, give me everything for this customer ID, but it's going to say, give me the type is order. And that is, all right, this is VM latency. Say again? I'm getting half. Yeah, so in that query, I actually did two separate queries. I did one to get customers, one to get orders. And then I said you have to merge them on the client side at some point. So in Cosmos DB, if you can join intra document, but if you to get that same join, we don't have that. You don't know the relationship between the customer and the order. It's not codified anywhere in like a key or anything like that. But actually, I'll show you here how you can get the customer and the order at the same time. So actually, I'll just do that right. Okay. Okay, I'll just move back to the portal since the VM latency in Visual Studio is pretty rough. Okay, so this ran, but let me just show you the query in the portal anyway. So here, all the data is in the same collection. So if I just run c dot c.id equals, let's say we did 12 before. Oh, okay, this is actually a different collection, so I need a different table. Okay, 66, that's a customer we know exists. All right. Okay, so now if I do this, oh my gosh. Sorry? Yeah, sorry about that. Okay, thank you, friend, kindly audience member. Okay, appreciate that. All right, so as you can see, now we're getting three documents back. The first one is we have the customer profile information, but we also have their orders with the same customer ID. So in this way, you've made one network call and you're getting everything back related to that customer. Does that make sense? Yep. Okay. All right. Sorry? Yeah, it is still 2 documents, so you may have to merge them on the client side, or maybe you've done something smart where you put in the order, you add in the information that you need. But now you've minimized the amount of network calls. You've gone from 2 to just 1. Okay. All right. Okay. Let me switch back to slides. Okay. Okay. So again, I have about 7.5 minutes left for this 45-minute talk, and it's going to cover partitioning. How do you feel like partitioning would be a valuable topic to go over? Yes? Okay, maybe I should have started with that then. All right, so what is partitioning and why is it so important? After data modeling, it's one of the most important things you have to think about when setting up your Cosmos DB cluster. So what is partitioning? Cosmos DB does horizontal partitioning, and that's the way it enables the scalability. So instead of having one giant machine that has all your data, that you put all your requests to it, if you split that data into different shards or partitions, then now each query can go to different ones, and now you get that horizontal scalability. So that's generally why you'd want to partition. But in practice, how do you choose the right partition key? This is something in Cosmos DB you have to choose up front when you make a new collection or container, so it's really important to get it right in the beginning. And what can go wrong if you choose a bad partition key? So the idea of a partition is that all your data with the same partition key value is in one place. So in my customers collection, say it's customer ID. So anything with customer ID Deborah will be in the same partition. So it's literally on the same physical server. Anything with customer ID Andrew will be potentially in the same server, but also in the same partition. So it's all grouped together in these partitions. But what can go wrong? If you choose, let's say, a bad partition key where when Cosmos DB does a query, and if you think about it, if you don't know which physical partition or which partition your data is on, you'll have to ask all of them. It's the same thing where if you, let's say you have like 5 friends and you know one of them has your phone for some reason, and you know who it is, you just go ask them, hey, give me my phone. But if you don't know who has it, you know one of your friends has it, you're asking all of your friends, hey, do you have my phone? It's the same idea with query. If you know the partition, you can go straight to that machine and get the data you need as opposed to doing the cross-partition query. At the same time, another thing you have to worry about that can go wrong, which we've actually seen a lot of customers hit, is we have a 10 gigabyte limit for logical partitions. So that means if your partition is ID and you have more than some reason 10 gigabytes of data for that ID, then that partition becomes full. So I'll show you some tricks you can do to make sure you almost never hit that 10 gigabyte limit. But if you end up partitioning based on something like timestamp, let's say you're an IoT system, you have machines or devices writing millions and millions of documents, and your partition is like the hour, you might actually fill up that 10 gigabytes without even knowing it. So that I'll show you some different choices for a partition key there. Okay, so quickly walk you through behind the scenes how partitioning works, and then go through some strategies for choosing the right one. I know we're running out of time, so please come see me afterward. I'm happy to follow up and, oh, someone's cutting, okay. Sure how that happened. Okay. Okay. Okay, my PowerPoint has crashed on me. All right, that's great. Oh, okay. All right, so how does partitioning work behind the scenes? I know the keyboard shortcut for this, I just can't figure it out on this machine. 3 there? Does that work? That didn't do it. Okay, here we go. Woo, all right, so how does partitioning work? Let's say you have a customer table and you have a partition key is the user ID. So it'll probably be a GUID, but let's just say it's a name. So what happens is Cosmos DB looks at that partition key value, so it's Deborah, hashes Deborah into, say, 100. Takes the word Tim, hashes it into 105. Andrew, 106. Basically some value that it's hashed into. And what Cosmos DB does is it then uses an algorithm to distribute these pseudo-randomly over different partitions. So what, for a concrete example, suppose you're taking the hash of the user ID and you're hashing Deborah. It goes into number 100, and then that falls into a certain range. So you have a range that might be 100 to 200, 200 to 300, 300, 400, so on. And each, depending on when the value falls, that's the range it belongs in. So this means if you think about from the partitioning side, all the data that goes with Andrew is in one logical and physical partition. This is one physical machine. All the data, Mike, same machine. Bob has a ton of data, so he's taking up this whole partition right now. But that's how the partitions are set based on the partition key. Okay. So what happens when partitions need to grow? So this is how we get the horizontal scalability. If you filled up literally the data on, or almost close to filling the data on one machine, Cosmos DB will proactively split that partition into 2. So what that means, it'll subdivide this range. So now, if the range before was 400 to 500, everything from 4 to 450 is now in one new partition, 450 to 500 in a separate partition. Subdivide, okay. Okay, so that's how partitioning works behind the scenes, but in practice, here are some principles of how you might choose a good one. So you want to choose a good partition key where you know if you divide all your data based on it, you'll get a good distribution of both storage and your request pattern. So here we have an example. It's actually a real-world scenario similar to what Toyota did for their connected car scenario, where they actually had to have a lot of vehicles emit device telemetry, and they had to choose a good partition key. So I'll walk you through some choices of partition key and why they may or may not be good choices. So for example, the first one, let me tell you more about the scenario. Scenario is you have each car, then they're emitting data to Toyota, and then if something bad happens, like an air bag goes off, then they can kind of send a message to the driver and make sure that they're okay. Or in the worst case, call emergency services. So one way you might partition is, okay, maybe the model of the car. So you have like these fake car names, models we made up, but if one of them is way more popular than the other, and that's the only car emitting telemetry, then all the data for that type of car is now in one machine, and that machine is going to fill up, and it's not going to be able to scale. So that's not a really great choice for a partition key in this respect. Another idea is the current month. Which is great for storage because if you assume each month you have roughly the same number of users, then you'll have roughly the same number of storage for each partition. But the problem is, what is the current month? It's the current month. So now all the data for the current month is going to go, again, to the same machine, and you're quickly going to fill up that limit again. So these are choices that probably won't work, but how about some better ones? One is the device ID. The good thing about device ID is that it's unique, and you'll get basically one device ID for, you'll get different hashed values for it. So if you think about hash of like a random device ID, hash of another random ID, hash of another random ID, throw them all together and distribute them in different ranges, you'll probably get, if it's random enough, even a fairly random distribution of the hash values into each partition, which means now all your data is divided relatively equally among all your partitions, and then when you do queries, you'll be able to distribute them among them. But at the same time, in an IoT scenario, suppose you have so much data for one device that it's going to exceed 10 gigabytes. Instead, what you might do is you can do like a synthetic key where you take the ID and then concatenate it with this maybe date or hour or maybe month here. So now you have basically expanded the space on which you can have data for that partition. Okay. Did any of this make sense so far? Okay, yes? Okay, great. All right, and this will be my last slide. I'll just talk you through some of the guidelines to pick a good partition key. So overall, you want to distribute the request and storage volume. And try to avoid hot partitions where all the data is going to one of the partitions. Okay. So what you definitely want to do is ballpark your basically really understand your workload and know your scale. If you know the number of reads and writes per second, if you know you have a write-heavy workload versus read-heavy workload, optimize for those. It's unlikely you're going to be able to choose one partition key that perfectly covers every single query. But if you can cover 80% of them and get efficient queries there, then that's pretty good for your system. Look at top 5 queries. This is actually the exercise we do with customers. Give us your top 5 queries, and then we look at the where clause. And if you're always doing where user ID is something or where customer ID is something, that ID might be a good place to start with a partition key. All right. Okay. And in general, sometimes we hear people say, oh, we have too many partition keys. It's actually great to have more. In fact, that's how we do the scalability. So the partition keys are just logical. Don't think, oh, if I have 1 million IDs, that's like 1 million servers. It's not. It's 1 million logical partitions, but Cosmos DB behind the scenes will have a more reasonable amount of physical servers. So there might be 5 or 10 or 20 that hold these 1 million logical partitions that are spread onto these smaller logical partitions. So if you remember one thing, more partition key values gets you a more scalable system. All right. So thank you so much for sticking with me. Cover data modeling, partition key. Please see me for any other questions. Thank you.